All right. Welcome back to the Piezo SHOCK Show. Today I'm going to be describing and answering a question about the different. Oh wow, how about that? About the different displacement. Won't you be using this again? About the different displacement values for different transducers. So there's a whole host of ultrasonic transducers you guys are probably aware of. They range from atomizers that you kind of found commonly in homes. There are surgical ultrasonic transducers. There are diagnostic devices, actually. There are acoustic devices, surgical. So there's a whole bunch of different devices. So let's talk about, in general, what are their displacement ranges at resonance. So whether it's like a 40 kilohertz um, surgical device or welding device, uh, or if it's a megahertz. So how about that? Or if it's a megahertz kind of a transducer that's perhaps either for atomization or for diagnostics. So let's just really generally give you an idea. All right, so let's start with ultrasonic surgical devices. They typically range in displacement from 10 microns all the way to 200 microns. I know personally from my experience in phaco emulsification, um, surgical handpieces meant for cataracts can go all the way up to 100 microns of displacement, but typically the usage range is probably around 60 or 50 microns of displacement at resonance. And for ultrasonic welding devices, their displacement ranges tend to be around 20 to 30 microns. And now, as we go to other devices that are not bolt clamped transducers, their displacement is much less because they don't have a horn. There's just the bare piezo being excited, so there's a lot of stress in the piezo. So um, in those cases, you'll expect at maximum a couple of microns. And if they're actually low power devices, maybe they're into sensing. Those are going to be into fractions of a micron of displacement. And what actually is really the reason why we need more displacement. So why are surgical devices, you know, hundreds of microns or sometimes tens and like let's say 100 microns, and we have a welding device which is only 30 to 40 microns, but the welding device is like, let's say, 500-watt transducer, whereas the surgical device, let's say, 5 watt or 10-watt transducer. So what's going on there? What's the reason behind the size of the differences between the micron range and the power? So power is not displacement. They are different things altogether. So the aspects which govern power is when the transducer is against a very heavy load, it will be able to continue to oscillate at 20 microns. Let's say when you're welding, when you're against a very stiff, metal workpiece, and you're trying to bond two things together, it will be able to have that displacement despite a very stiff resistance. Um, However, if you took the same surgical transducer and you put it up to a metal kind of workpiece, it would not be able to provide 100 microns. It provides that micron range against the intended load. So the intended load for a welding device may be very stiff. Let's say if it's metal welding, or there may be a large area, for example, for plastic welding, there may be a larger area. For surgical devices, they we're more interested in the range of displacement, which also increases the amount of energy absorbed. But that range of displacement can then occur with less power. You don't need as much power. You don't need a huge transducer. You need something better suited for, obviously, the constraints of being in a surgeon's hand, and also the micron range, which is able to give you the intended effect. So the intended effect, for example, atomization, that micron, that displacement range is going to take a lot less amplitude, as well as the diagnostic devices, the sensors. They will also take a significantly lower displacement level. So those are just the ranges. You're not talking about millimeters or centimeters of displacement for ultrasonic transducers. You're looking at like 200 microns and lower. the larger the transducer, typically the lower the frequency. And if you have bending, for example, in some ultrasonic transducers, surgical transducers utilize bending. In those cases, you can have up to almost 500 microns, I believe, but that's kind of in a rare case. But typically sub 100 microns, and sub 20 microns is a kind of a reasonable kind of area to work in. But just keep in mind that with changing frequency, you significantly change the velocity, and a lot of times the velocity is what you need to be analyzing, which can go into for the ranges I mentioned, which can go into tens of meters per second for some of these devices. If you have 200 micron at, let's say, 30 or 40 kilohertz, you might be able to get into several meters per second, which is important for speccing out a laser vibrometer. So I hope this helped just give you a general idea about displacement ranges in ultrasonic transducers. All right, so thanks for tuning in, and I will see you in the next video.